and horizontal angles of the windscreen are specified so that each pilot has a sufficiently extensive, clear and undistorted view to be able to safely perform any maneuvers within the operating range of the aircraft. It is important that the pilot has his seat in the correct position to get a good view forwards and downwards out over the window, over the coaming and nose of the aircraft, without restricting his overall view. To help with this, reference eye points are often painted on the flight deck windscreen frame. On some aircraft, an opening window to the side of the windscreen, known as a direct vision or DV window, is provided to enable the pilot to have sufficient visibility to land the aircraft safely should the windscreen become obscured. These windows are also sometimes used as emergency exits. Passenger cabin windows are designed to be fail-safe and normally have two panes of acrylic plastic mounted in an airtight rubber seal fitted into a metal window frame. The inner and outer panes are each individually capable of taking the full cabin pressurization load, so if one pane fails, the other will prevent loss of cabin pressure. The wings support the weight of the aircraft in the air, and so must have sufficient strength and stiffness to be able to do this. Their strength and stiffness is determined by the thickness of the wing, with the thickness and type of construction used being dependent on the speed and weight requirements of the aircraft. The types of construction are biplane, braced monoplane, and cantilever monoplane. Very few biplanes fly at more than 200 knots in level flight, so the air loads are low, which means that a truss-type design, which is covered in fabric, is satisfactory. The wing spars, interplane struts, and bracing wires form a lattice girder of great rigidity, which is highly resistant to bending and twisting. Unfortunately, this system also generates a relatively large amount of drag, which accounts for the fact that biplanes fly relatively slowly. In flight, the flying wires hold the wingtips down and support the fuselage. On the ground, tension in the landing wires supports the wings. In the braced monoplane type of design, the wing is connected by a brace to the fuselage or landing gear. In flight, the brace is subject to tensile loads and acts as a tie. On the ground, it is under compression and acts as a strut. To provide fail-safe protection, the brace is often made from more than one member. The Shorts Skyvan, for instance, has 3 members per brace. This type of design is mainly used on low-speed aircraft. Now we will look at cantilever wings, the design used by most modern airliners. The wings have to absorb the stresses due to the lift and drag in flight, and, if of this design, their weight when on the ground. This is achieved by building the wing around one or more main load-bearing members known as spars. The wing spars pass from wingtip to wingtip either as single structures or as connected sections. The spar will normally be an I-beam either manufactured as a single part or made up of two or more parts to give it fail-safe characteristics. These are constructed so that they will absorb the downward bending stresses when on the ground and the upwards, rearwards and twisting stresses when in flight. In flight, bending stress relief is provided by mounting engines on the wing and by locating the major fuel tanks in the wing. Fuel usage procedures are designed so that the wing tank fuel is used last. This is of particular importance at high all-up weights, when the outer wing fuel tanks should be full. As fuel is used, the weight of the aircraft decreases, which reduces lift required and therefore the wing bending moment. The wing may be of a single spar, twin or multi-spar construction. A conventional structure would consist of front and rear spars, stringers, and ribs, with the metal skin attached to them to form a torsion box. The torsion box functions as a beam, but is considerably lighter than a solid beam of the same size, without losing much strength. The stressed skin takes the loads due to the differences in air pressure and the mass and inertia of the fuel in the wing tanks. It generates direct stresses in a span-wise direction as a response to bending moments, and it also reacts against twisting forces. Stringers are span-wise members which give the wing rigidity by stiffening the skin in compression. In most modern aircraft, they are formed by machining integral ridges into the skin. Ribs maintain the aerofoil shape of the wing, support the spars, stringers, and skin against buckling, and pass concentrated loads from the engines, landing gear, and control surfaces into the skin and spars. Ribs often have lightning holes cut into them. As well as reducing the weight of the structure, these holes are usually flanged to help stiffen the rib. The major structural components of the wing are generally manufactured from aluminium alloys. With composite material, such as glass-reinforced plastic or carbon-reinforced plastic and honeycomb structures, being used for more lightly loaded structures. Carbon-reinforced plastics are gaining wider acceptance for the manufacture of major structural components, such as the fin and horizontal stabilizer. There are a number of aircraft mass limitations that you must become familiar with. The maximum zero fuel mass of an airplane